In today's lesson, we're going to talk about vectors and scalars, which is a huge part of physics. It goes through the rest of the entire course. So as you can see on your screen, vector quantities have both magnitude and direction. And that's something you're going to need to know. I'll ask you that frequently, and you will always need to respond with magnitude and direction. It says that traditionally the variable in the problem, if it's a vector, gets a half arrow over the top of it. So what they're talking about is something like this. If you had vector A, then you would put this half arrow over the top of it. If you have, vector B, you put a half arrow over the top of it, so on and so forth. A scalar is something that only has magnitude. It does not have direction. If you were to put it on a graph, as you've done in algebra, it would not change if you rotated it, reflected it, translated it, or transformed it. It doesn't do anything to that quantity. And less often seen, but still seen, if you had scalar A, sometimes they will denote that it's a scalar by putting a dot over the top of it. Examples of a vector would be velocity, displacement, or force, and scalars, distance, time, and energy. There's obviously a bunch more for both of those, but that's just a good example. Parallel vectors can be added to each other using the head-to-tail method, or sometimes it's called the tip-to-tail method, depending on which book you look at. So I call it the head-to-tail method because that's how I learned it. Alright, so let's look at the first case here where both vectors are traveling in the same direction. Remember, vectors have both magnitude and direction. I've given you the magnitude over the top of each vector, and I've shown its direction by adding heads to the line so that you know which direction the vector is pointing in. The first thing that you need to do in any physics problem is always decide what your coordinate system is, what's your reference point. So we're going to say in this physics class that moving towards the right is positive and moving towards the left is negative. That's standard in most physics classes. So with that being said, we have this 5-meter vector traveling in the positive direction, and we have this 2.5 meter vector traveling in the positive direction. So if we use the head-to-tail method, this is the head of the vector and this is the tail of the vector. And if we want to add these two vectors together, then we will take the tail end of this vector and place it on the head end of this vector. And if you do that, we get this component vector down here that's got both of them in it. So we have the 5-meter vector and we have the 2.5 meter vector added together to give us a 7.5 meter vector. Alright, let's look at the second case. Again, we have a 5-meter vector traveling in the positive direction, and we have a 2.5 meter vector, but this time it's traveling in the negative direction. So when we add those head to tail, we see that the net vector that we get is this 2.5 meter vector component down here, because 5 minus 2.5 is positive 2.5. We are still adding these two vectors together just as we did up here, but when you add a positive to a negative, it's really subtracting, and so this gives us our overall vector. That's if the vectors are parallel to each other. Let's see what happens when they're perpendicular. Here we have two vectors that are perpendicular to each other. Okay? If we want to add those, we're still going to use the head-to-tail method. Notice right now they are tail-to-tail. So we need to move the vectors. And that's one cool thing about vectors, is that they can be moved around the space and it doesn't change the problem. So let's take that vector and drag it up to the top here. They are the same vector. We're now just going to ignore the bottom one and use the top one. They're both 5 meters long, and now we have it in the head to tail fashion. The next thing that we need to learn how to do when it's a perpendicular vector that we're adding together is we draw a line from the beginning point to the ending point. Alright, so let's get our line. Alright, and put that in here. So now we have our resultant vector. That's what this is called. And oftentimes you'll see it with the R and the little half arrow that we are used to putting in there. Okay, so this is how we add perpendicular vectors. Now the thing is, we have to figure out what the magnitude and the direction of that new vector is, that resultant vector. To get the value of r, the resultant vector, is quite easy. Hopefully you can see that this is a right angle, which makes this a right triangle, and we can use the Pythagorean theorem to find out this hypotenuse, and that's in fact exactly what we're going to do. So we have 5 meters squared plus 3 meters squared equals our resultant vector squared. Okay, so this is obviously 25 meters squared. This is 9 meters squared, and whatever that is going to be our resultant vector squared. So we get 34 meters squared equals the resultant vector squared, and we don't want the resultant vector squared, so we can say the resultant vector is equal to the square root of the resultant vector squared, which is equal to the square root of 34 meters squared. Alright, so that means that the resultant vector is equal to 5.83 so on and so forth meters. You'll notice up here that our sides have only one significant digit, so that means our resultant vector can only have one significant digit. So our resultant vector then is equal to 6 meters. Alright, so that's the magnitude of our resultant vector, 6 meters. Now we need the direction. Alright, so the direction is this angle here. Alright, and the reason that I chose that angle is because I'm saying that this is our coordinate system that we're used to. We've got our x and our y axis. Okay, and remember, from the unit circle, that's north, that's east, south, west, and our angles are on there also. This is 0 degrees, and it's also 360, and this one is 90, 180, and 270 down here. Alright, now notice that I've drawn this little arrow showing that I want the angle coming up from 0. So I'm telling you to give me the angle in reference to 0 degrees. Okay? So in order to do that, we need to use our trigonometry. So since we're going to be using the trigonometry or the trigonometric functions, let's go ahead and write in SOHCAHTOA. And then remember what I said about the vectors being able to be moved around. We have this vector here and this vector here, and it's part of this triangle. But the angle I'm looking for is this one. So I could form a new triangle if I just took this vector and slid it over here. So let's do that. Alright, and that is our 3 meter vector. okay? And our hypotenuse is still the 6 meters. Now, when we actually, if we use the hypotenuse, we can't use the 6 because that's been rounded off. We'll have to use the one we get from the calculator. Alright, so let's see here. Remember, if there is ever an angle or a triangle that you're going to use trigonometry on, you're going to need to name that triangle based off of the angle you're talking about. So that means that this is the opposite side, this is our adjacent side. Alright, and I want to figure out what the angle is. I don't want to know what the side is. I know what all my sides are. So remember, when you're trying to figure out an angle, you use the inverse trigonometric functions. So I've got an opposite and I've got adjacent at my disposal. So that looks like we'll be using the tangent function. So let's go ahead and write down our tangent function. We've got theta is equal to the inverse tangent of the opposite over the adjacent. So the opposite is going to be our 3 meters and our adjacent is going to be our 5 meters. So when we type that in a calculator, we get 30.9637563 degrees. Okay? Now, the significant digits for our angles. We didn't get any other angle in our problem other than the fact that we had a 90-degree triangle, a right triangle. So I think for us, we're going to just do 2 significant digits for that in order to make sure we don't say that we're more accurate than we actually are. So our angle theta is going to have a significant digit here and here. That's the first one, that's the second one. But you have to look one spot over and see if this 9 does anything to the 0. And it does. We're going to end up with 31 degrees as our angle. Now that's 31 degrees from 0. Alright? We could have just as easily described the position of that new angle here and say that was the theta we were interested in, or we could have said this theta up here if we wanted to, although that one might have been a little bit more difficult to describe. So let's go ahead and describe it based on this theta 1 here. Alright. Notice how the arrow is pointing down and away from north, and it's pointing towards east. So we would know that it would be east of north. Whatever the angle is going to be east of north. And you know that this whole thing here is 90 degrees. We just figured out that this angle is this 30 point blah blah blah. So 90 minus this gives us this angle. And that is 59. Let's see, where can I write this? Theta 1 is 59.0362437 degrees. And so with 2 sig figs, that's just 59 degrees. And that one, we would have to go on and further say east of north, because we are moving in the easterly direction away from north. Alright, so in order to completely say what this vector is, in order to name that vector, just like this one was 5 meters in the positive x direction, or you could have said 5 meters east, and this is 3 meters in the positive y direction, or 3 meters north. It has magnitude and direction. Our resultant vector has to have magnitude and direction. So we would say 6 meters at 31 degrees from 0, or it could be from the positive x-axis, or it could be at 59 degrees east of north. All of those are valid directions and give us a complete answer for our resultant vector. Alright, that's all for this one. I thank you for learning with me, and I will see you next time.